Hello there, welcome to another concept session. So today we are going to tackle a little bit more difficult problem along the lines of problems which involve thinking in terms of non-inertial frames. For inertial frames, so, it's rather simple. Second law for a particle of mass m is just F equals ma. I mean, you can write this as dp dt, if you like, with the p is equal to mv. And because we're talking about one particle, that's how Newton's second law should be written first for a single particle. So for that, it doesn't matter how you write it. And because m is constant, take a derivative, m comes out, and then use acceleration. Just definitions. So in an earlier video, I already covered that in a non-inertial frame, like a frame which is accelerating with respect to an inertial frame. So this is an inertial frame, and this is a non-inertial frame. Now, what is inertial frame? Well, a frame with respect to the absolute at rest in the universe, a frame which is absolute at rest in the universe. This frame moves with either is at rest with respect to that or moves at a constant velocity, whichever way, just constant velocity, right? So in that inertial frame, that's the case. If a frame is accelerating with respect to any of the non-inertial frames, if accelerating with respect to the frame at rest, well, then it has some acceleration, but it has the same acceleration with respect to any other inertial frame. You can just do time derivative and you can figure that out. Okay, so that acceleration, when you work it out, what the same particle, its acceleration in this frame may look like a prime, and then if you write what the mass time acceleration will be in this frame, in the non-inertial frame, you will find that you need to modify your force. This is the original force, so-called real force, and this minus this whole thing is called fictitious force. Fictitious force. So here is that fictitious force is simply mass times acceleration and negative signs. So if it's accelerating that way, then fictitious force is like the problem has another force than all the real forces, is mass times the acceleration, opposite to the acceleration. So if so the frame is a truck which is accelerating and the object is a box on the truck, then there, if you're looking at the box from the perspective of truck, it will seem like there's a force towards the back of the truck. Okay, and there are examples, so see earlier videos in this series. Today we want a little bit more complicated problem. So I have a frame, and the other frame, instead of just translating, so this is a translation. So this will be something that will be applicable to translating frame. Now, if something is just rotating, and of course if something is rotating and translating, you have to have both of these things, right? But something is just rotating, so we'll keep the origins of the two frames fixed, and we also keep one of the axes fixed for simplicity. Okay, when you do a calculation, suppose this frame is rotating with respect to the fixed frame, the inertial frame, so without the prime, and this is omega is the rate of rotation, angular velocity. So for instance, this frame, x prime, y prime, z prime frame, would have rotated with this in time delta t by this angle. Delta theta will be that much. Okay, so when you work it out, we'll work it out, the answer will look something like this. So in the inertial frame is the same thing as that, but in the rotating frame, of course, the acceleration will be this of this particle, but then you'll have all these other forces. So this whole thing is one fictitious force, this is another fictitious force. So this minus this thing, this is called Coriolis force. And this is called centrifugal force. Okay. And how do they arise? Well, we would be able to see it by the end of today's lecture. Okay. It's not surprising, right? It's rotating, then it's also accelerating. So you know from before that suppose a particle was just rotating and I was in this frame, and say this x, y was this, and the z was pointed out, and this particle is, say, rotating, then at a constant speed. This is just an example. Then the acceleration is pointed to us, this origin O, right? If it's over here, it's pointed about this. This acceleration is actually changing in direction all the time. It's pointed this way, pointed this way, over there. But this is, when something is going around, is when something is rotating, it's actually accelerating. Particles are accelerating. So when you're rotating the frame, this frame is also has an acceleration. Oh, I forgot to write m's here and m here. So you might say this whole thing are the fictitious forces. So you if you want to write it like this, minus m times some a, you just figured it out, and that a, it just happened to be 2 omega cross b plus omega cross r prime. And then this way of writing is the same as that way of writing, but behind this a there is all this extra structure, because it's not just, we don't know what the acceleration of the frame is, as opposed to given here you're given the acceleration of the frame. Over here we just told is rotating with omega, and because rotating it will have some acceleration, and you got to figure out that acceleration. What is the acceleration of the frame that you need, so that the equation is consistent with equation in the inertial frame. All right. Okay, so I just drew some pictures to help us and reduce the time in writing. Okay, so in the rotating frame, we just covered that we are going to see something like this. So I haven't told you how I got this, right? But you're going to see something like this. Okay, so let's imagine, for simplicity, that the particle is at point P at time t, and that point P is in xy plane, and the way that frames are rotating, that they're both their xy planes, xz planes are the same. So this thing just written out here, this thing is that plane. The particle is in that plane at that instant. So both these people, say you are using xyz plane, so you think it's over there at P, so that's OP for you. And if you're x prime, y prime, z prime plane, you also see it's at OP. So they're the same vectors, right? Now when you rotate, you mark the point in the xz, you mark the point on the xz plane where, so say you are using, let's call O and O prime. So O prime, X prime, Z prime, Y prime, you mark the dot in X prime, Z prime plane with P prime. So your P prime is kind of fixed where it is, okay? Right? It's in XZ plane. But at time t plus dt, the particle has moved. So this particle is like, maybe it's kind of moving like this. So it moved from here to there. At a little bit later time, it's over here. You noticed in the fixed frame that your new vector, position vector is this, new position vector is this, old position vector is this. So you can write down, hey, in time delta t, delta r is rt plus delta t minus rt. No, this is just a old, same old thing. So this vector plus this vector equals to this vector, and so you write like that, vector triangle. But you're using this frame, you're in the rotating frame. What you can notice that it hasn't moved P to Q, it moved a P prime to Q. For this Q at time t plus delta t is the same in both frames. It's at the 2 at some point Q. So you're going to get this vector delta r prime for you will be r prime t plus delta t minus r prime t, but this r prime is not equal to this r prime. So here it looks like r prime t is equal to r of t, but this r prime, I should say r prime hat, r prime, which is rotating away from the original place it used to be. But because I'm in the rotating frame, I remember it's in the x prime z prime plane, but I'm not aware in this calculation that is moved away. I have to use where that point I marked was, and that point has actually moved with me, so it will be a little bit different. Okay, so if you look at what P to P prime is, well, how much distance I have to correct for between this and this. They're different, but how much different? Well, you just have to see that the vector actually, that vector is rotating with, that vector is rotating with the rotation frame, and you can see that that point P prime used to be together, but P prime start to separate on a cone. And if this is what used to be r vector, and so and this is the z-axis, so rotating about z-axis. So then is the arc of this circle, and this angle is rotated is omega delta t, right? So this will be r sine theta. This distance will be, this will be r sine theta times omega t, times delta omega delta t. This is the theta, this is the radius, and this is the delta theta. That's the arc. So that's the distance is rotated. So that's how much is the different. This delta r prime has to be. But at this instant now, just like over here, on the instant match, this vector is the same as this vector, so we can say this is same as r of t plus delta t, because I'm not comparing back at this instant. This at time is t plus delta t, so the position vector at any instant in the two frames will be the same, because I'm using the same O, and O prime is the same. Okay, but when you're comparing two different things, it will be different. So let me use this fact. This will be r of t plus delta t, and then r prime of t, and this will be the p prime vector. So this is the current. So this is my r prime vector. So this r prime is that O to p prime. So this is O to p prime, which is now. So this will be r of t plus delta t minus r of t, this original r of t, plus p to p prime vector. So I need a vector. So I know the magnitude is this stuff. I need to write p to p prime as a vector. So if you look at, if you denote this as the omega vector, this is a rotation, of course, but if I think of this as a vector along the axis of rotation, so this is something I introduce, and it's very useful, handy thing. So this vector and this vector, if you cross product it, if you look at omega cross r, so you have this vector omega, and the r vector is that way. When you cross product it, then this becomes omega r, and this angle, say, is theta, sine theta. So that's the magnitude, and you do right hand rule, and right hand rule shows the direction is that way. So if you go like this, direction is coming out, right? Direction is coming out. Okay, but that's nothing but it's the same thing as that. So omega cross r, so this pp prime is just omega cross r. So these are the vectors in the inertial frame, and this is in the non-inertial frame, and you can clearly divide this thing, everything, by delta t, and take a limit delta t goes to 0. So this says this original vector that we had, its rate of change versus the same original vector its rate of change in two different frames. So moving this guy on the left side and this guy on the right side, what do we get is delta r, delta t, inertial frame, that's this stuff, is equal to delta r prime delta t in non-inertial frame plus omega cross r. And at this instant, it's at instant t, at t. So there's no distance between r and r prime, which you look at one instant, right? So the rate of change of the vector in two frames are different. So this is true for every vector, actually, not just for r vector, because we just use the geometric properties here. So for any vector, if I look at some vector b, and it depends on time. So this vector b, its rate of change, this vector b at any instant in inertial frame is the same as in non-inertial frame, in rotating frame. But the rate of change, dB dt, if I evaluate was in the inertial frame, is going to be same as dB dt. We can just drop the primes, and often it's okay to drop the primes. as long as you put this, where you're doing this, plus omega cross that same vector over there. And you can see the units of time will be same. This is 1 over time, so this will be b over time, this is b over time, this is b over time. So, and this is these are going to be our operating equations from which we can deduce all the other things. Okay, so if you understood these things, you can actually build up and get this this result in the final. Okay, so we have a RT in the inertial is RT in the rotating frame. Same, because their origins are same. So this is inertial x, y, z, and this is x prime, y prime, z prime, and this is same as that. This is omega delta t, and this going around at omega, and omega vector is that way. And if the particle is over here, then this vector from common O prime, that vector is r of t, and they're same vector, same direction at instant t. Then no need to write more complicated for primes and things like that, right? Although we wrote primes here, we can just drop the primes as long everything is rotation frame. So you can do everything is in the rotation frame. Okay, and this being constant. All right, so take a time derivative of this vector dr dt. That's going to be velocity, inertial velocity will be, if I do an inertial, which we just found out from here, this will be dr dt in the rotating frame plus omega cross r, and so this is just equal to, this one is the velocity in the rotating frame. So velocity of this particle m at instant t in the rotating from with respect to the prime frame plus omega cross r. R is same as r prime. So if you wanted to write very verbose, you could write this as vt plus omega cross r prime. You could write like that, it will be fine. Okay, how about acceleration in the initial frame? That's the one that relates to the F equals ma, right? So that's equal to dv in, take this guy, take his time derivative, or inertial. Well, we have this formula, we can just plug in there. So going to be dv rot dt inertial plus d dt of omega cross r, and do it inertial. So these derivatives are inertial derivatives in the inertial reference frame. So we know derivative inertial frame get extra thing added when you relate to the rotating frame. So we want to write everything in the rotating frame over here. So this guy, let's work out that one first. So we see I'll get a same derivative in the of the same quantity but rotating frame, plus I've got an omega cross v rod. So you're going to get these two terms, right? And over here this is constant, so we can just kind of slide this omega cross. So this is same as before, so I get an omega cross. For this thing, I'm going to get dr dt in the rotating frame plus omega cross r. So that's this whole thing is going to turn out to be 2 terms, and this is nothing but v rod. So these 2 v rod add up. So I have this is just acceleration in the rotating frame plus 2 times omega cross v rod plus omega cross r. We need to keep a parenthesis because we need to do this omega cross before I do omega cross, okay? So we have this, and then from there we can immediately get that, okay? So for the inertial frame, for the inertial frame, the law is very clear. So we start with inertial frame law, F equals to mass times. This is very simple, straightforward, the same old law. Then we put this whole thing over there, m rotation frame plus m, all this fictitious thing from here to there in here. And now bring fictitious forces to the left. We will have F minus 2 omega cross v rod minus 2m, not 2m, m omega cross r equals m a rod. And so this will be the law. And of course this is more complicated, but once you have a problem to apply to, it's not that complicated to apply, and we can apply to a couple of problems now. Okay, so I hope you understood this, and I'm going to do some examples. Okay, so here is a simple example. Not so simple, I guess, but it is an illustrative example. A bead is on a rod, and the rod is going around at constant omega, and this is a frictionless. We're supposed to find all the forces and where the bead will be at certain instant t if it was at this place at time t equals 0 at rest. And we'll say just it suddenly started to rotate, and okay, so how do we find it? All right, so you already know that there will be a force of gravity. So this is z-axis, and this may be any other direction. This may be y-axis, this may be x-axis, and this is some time. And these you can say primes, and they're rotating. This is a rotating frame, So we are not going to really need to simplify it. I mean, you could actually say this is along the x-axis, the rotating frame. I'm going to write everything in the rotating frame, okay? And see what happens. I'm going to solve the problem in the rotating frame. It's up to us what frame we choose, okay? You can solve this problem from the inertial frame perspective also, by the way. And it's not that difficult, but for the sake of practice, let's do it in a rotating frame. I'm going to insist that I'm rotating with the rod. So I'm going to say a frame rotating with the rod. And I often, when I do that, I said, hey, why not just, the rod is straight forward, so why not I just say, this is my x-axis. I'm only gonna move along the x-axis. The bead is going to only move along the x-axis. It's not going anywhere, right? So when you look at R, what happened? When I look at R, at any instant t, I'm in this frame, and this x prime, which I can just drop that prime. I'm just going to drop the prime, and this is going to be just x of t, and that's my I hat, which is prime, same as I'm going to draw the prime I hat. Nothing else going to be. X can be, wherever. X can be on the rod. If the rod is finite, then it can only be up to whatever the ends of the rod are. Okay, so I have this, and so if I do the velocity, and which is same as rotating velocity, velocity in the rotating frame, so this just be x dot or dx dt dot equals to d dt I hat, and the acceleration, this acceleration in the rotating frame will be another derivative of that. At any instant, it will be x double dot I hat. But we'll have all of these other guys. The force will have mg. One of the normal will be from the bottom or support part, and this guy, you will see that. Let's look at the direction. So omega cross r. So this along I hat, and this along z hat, and this along z hat. Just the direction part. When you do this out, it's going to be minus plus j hat, and when you do this out, it's going to be minus I hat, and with this minus, so with this minus, it's going to be plus I hat. So it's going to be pointed towards that direction. So this whole thing is F centrifugal force. So F centrifugal force. Its magnitude will be omega square x, because R is just x. So omega square x. How about this, guys? Minus omega cross v, 2 omega cross v, m, minus 2m. Just direction part will be k hat. The v hat is just I hat. So it depends on sign of this, right? But I'm just going to look at the vector part, I hat. So k I hat is j hat with a minus, so minus j hat. So x is that way, y would be that way. Then this is the direction in which your Coriolis force is. Seems if something is so if positive, then it will be this way, then but acceleration is only this way, which means there will have to be a normal force opposite to that. So we see that normal force has to balance Coriolis force, and this is positive of that, and magnitude of that has to equal to magnitude of that, and we see that n1 is equal to mg, because along the z-axis is along the y-axis, along the z-axis, but along the x-axis there is going to be there's no x for forces, there's no x for that guy, so there's x only for that, and from there we have m omega square x equals to mx double dot. So this one we need to solve using the initial condition, right? So the m goes away, so the x equals to sum a e to the power of omega t plus sum b e to the power of minus omega t. Okay. Then x dot equals to omega a e omega t minus b e to the power of omega t. Now at t equal to 0, initial condition is given, so the x becomes r0, a plus b, and this one says this becomes a 0 equals to omega a minus b. So this is not 0. Then a equals to b, and so the a equals to b equals to r0 over 2. So this gives us x at any time is r0 over 2 e to the power of omega t plus e to the minus omega t. It's basically r0 cosine hyperbolic omega t. Okay. N1 we already got that. N2 is Coriolis force becomes magnitude becomes m 2 times m omega times v. So omega is along the z-axis and v in the xy plane, so there's no sine theta there, okay? And v is, magnitude of v is x dot. We're looking at magnitude, so we can just erase this, so we're looking for magnitude only. So 2 times, well, if this is the x, so we need to get x dot is going to be omega 0 r0 sinh omega t. There's a minus sign there when you take a derivative. So this will always be positive, right? Because it's the x. Oh, there can be you have a positive here, negative here. So when the time gets negative, it can be negative. This can become bigger than this. Okay, x dot is omega 0. Oh, there's not omega 0, it's omega. So you have a 2m omega and another omega square r0 sinh hyperbolic omega t. And it's t greater than 0, we are assuming. So we got the force, we got this force, we got the Coriolis force, and this is the centrifugal force. So F centrifugal is going to be m omega square times x. So m omega square r0 cosine hyperbolic omega t, t greater than 0. So we got the centrifugal force. We got all the forces. They were pretty cool. You can do it a little more generally rather than assuming along this. You can do it in a polar coordinate with a radial direction in radial unit vectors. But sometimes you don't have to actually use the most general structure you know. You can pick a moment and a time that's general enough so that you capture all the physics and you're not kind of leaving out something. And still the calculations are done in the most simple frame possible. And if you try to do this problem in a non-rotating frame, it's a little bit more work in a different way. In my mind, there's not a little bit more work. It's in my mind, this problem is so simple that the work difference between the two approaches are more or less the same. And this example is only for illustrative. The power of using the rotating frame will become apparent when we do a little bit more complicated problem. For instance, if we go do Foucault pendulum, you might have gone to some museums where you've seen a very tall pendulum swings back and forth, but actually doesn't remain back and forth. That back and forth is the plane of that back and forth is actually moves with time. And the question is how to explain that. We will do that problem in another video. For now, this is it. If you like this kind of detailed explanation, getting into the weeds, you can check out my website. I appreciate if you can like these videos so you can get more distribution. Take care. Bye.